just because some of us just got done with Chem 1. This should be pretty fresh. Some of us, it might have been a couple moons since we did Chem 1. So let's just recap some of the basic principles, and we'll go from there. All right? Again, ask questions if you have any. All right. So, the review. Let's go to a periodic table. Now, there's a couple periodic tables out there. I have web elements up. There's this one. There's other ones. There's probably a periodic table that there's a bunch of periodic tables. They're very similar. There is a change. Let's see if I can get a different one. All right. So this is perfect. So the P table, right? And this is probably a very good one for you guys to use. But if you look, lanthanum through lutetium is all down on the bottom. All right. That's 15 elements. All right. On this web elements, there's only 14, and it starts with lanthanum and goes over to ytterbium, and then lutetium's up here. There's other periodic tables they have. They've changed it too. So there's a movement to make, because lanthanum and actinium used to be right where the 1 star and 2 stars are, changing it because of how atoms behave electronically. I'm not too worried about that, okay? So if we go back to this dynamic one, it tells you a lot if you click on it. So let's look at hydrogen. It tells you, it gives you properties, it gives you the group, S block, electron configuration, electrons, it gives you all sorts of properties, charges, all right, gives you kind of nice, all right. Now that's from Wikipedia, so I don't know how great that is, but all right. Tells you if you want alkaline earth metals, actinoids, transition metals. It's kind of nice. All right. So anyway, periodic table. Group 1, if you remember, group 1 are the alkali metals. Group 2, alkaline earth metals. Group 3 through 12, transition metals. 17 are the halogens. 18, noble gas. And if you look, they actually have the names that we don't, like chocolate gems, we don't actually say that much, but they're there. Lanthanides are down here, and actinides are at the bottom. All right. Charge of group 1, if you remember, +1. Charge of group 2 is +2. Scandium's always +3. Silver is +1. Zinc and cadmium +2. 13 likes to be +3, but as you guys remember, aluminum's always 3. Boron special. Aluminum is always 3. Gallium, indium, and thallium can be 1 or 3. So they're usually 3, but they can be 1. Carbon, ±4. Actually, tin and lead, as you know, are +2 and +4. -3, and these are positive. -2, -1, 0. 7 diatomics: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Right? And this one is nice because the liquids are blue. Bromine and mercury are blue. Some of the special names: remember sodium, Na. K, potassium. Iron. Copper is technically special. Right, copper, silver, gold. Remember, they go down in order of value, because a lot of times people see Ag and they think gold. It's argentum, I believe it is. It's not gold. Aurorum's gold. You got what other ones? We have tungsten here, thallium, lead, tin, antimony. But you guys always you'll be able to use a periodic table, so you'll have the names. So don't stress too much about the names. Diatomics, the charges are important, right? Because zinc and cadmium are always +2, silver is always +1, scandium is +3, aluminum is +3, because then they need Roman numerals in here, right, when you name them. So, and when you look at this, you got lithium, right? If I'm looking at lithium, that 3 in the top above the L is the number of protons, atomic number. 6.94 is the mass, right, which is the average of all the lithiums, the weighted average. All right, so let's go back to this review here. So I want to know protons, neutrons, and electrons. Protons, that's the atomic number, right? So when we have element X here, our protons are down here. Our neutrons and protons are up here. All right, they're up there in the mass. And then the charge, electrons minus protons. All right, no, protons minus electrons. Did that backwards. Yeah, because if I have the left side, I'm positive. Yeah, there it goes. All right, so magnesium. How many protons? 12 protons. How many neutrons? Well, 24 minus 12 would be 12 neutrons, right? If I have 12 positives, right? Because protons and neutrons are the ones with mass. Electrons technically don't have mass. They're 1,000 times less. Electrons, we have 12 positives and 2 more positives. We have 10 electrons. All right? And that makes magnesium 2+ is isoelectronic with neon. That's good. Selenium, protons, 34 protons. Neutrons, well, 79 minus 34. What is that, 45? And we have 2 extra electrons, so that's what, 36. There we go. Nickel, 28 protons. Cancel. 28 protons. Neutrons, is that 31? Neutrons, and then what, 26 electrons? And last but not least, we got the isotope of hydrogen called tritium. Of course, hydrogen has 1 proton always. In this case, it's 2 neutrons. And it looks like it has 0 electrons. So hopefully that makes sense for everybody. Hopefully that was a refresher. All right, number 2. And just so we know, full disclosure, math is not the hardest part about this class. Reading comprehension, the language, English language, word meanings, that's the hardest part about the class, not math, right? Because you have these devices right here, these calculators. Math is not a problem, all right? You can even use Microsoft Excel as your calculator, if you know that, which in theory you should, but I don't know if that's the case with CS 110. So math is not your limiting factor. It's pretty much the English part. Naming. All right. So we go back to our table. All right. Not hydrogen, but lithium down to francium is always +1. They don't need a Roman numeral. Beryllium to radium, +2. Do not need a Roman numeral. Scandium is +3 always. No numeral. Silver is +1. Zinc and cadmium is +2. Aluminum is +3. So everything else, not necessarily boron, but germanium and antimony, all right, below the stairs. So the stairs go between boron and aluminum, right? That separates things. So even antimony and germanium, everything else over to group 3, including the lanthanides and actinides, except for aluminum, zinc, cadmium, silver, and scandium, they need Roman numerals for their charge because they can have more than one possible charge. So copper type of compound is, well, opposite side of the stairs, opposite parts of the table, it's far apart, it's ionic. I have a metal, copper. Copper needs a Roman numeral. So I know iodine is -1, right? Because nonmetals do not change. So A would be copper 1 iodine. Copper 1 iodine. All right. Copper for B, ionic compound, metal, non-metal. Iodine is -1. So that means if I uncross the charges, I have to have copper 2. Iodine. C, cobalt. Iodine. Well, cobalt is a metal. Iodine is non-metal. Opposite side of the stairs, it's ionic. Cobalt needs a Roman numeral. So iodine is -1. So that's cobalt 2 iodine. D, sodium. Sodium does not need a Roman numeral. And I recognize CO3, so it's sodium carbonate. E, sulfur and nitrogen. They're nonmetals. Prefixes. Tetra for 4. Tetrasulfur. Tetra nitride. Right? So use the prefix, element first name, prefix, second name, change the ending to "ide." And if we remember our prefix, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. There are more, but we're going to stop there. F, sulfur and fluorine. Well, that would be sulfur. We drop the mono for the first, right? Because if I say sulfur, there's 1. Sulfur 4 tetra fluoride. NaOCl. Well, that's a metal and a polyatomic ion. Sodium. Hypochlorite. H, barium. Barium is a group 2 metal, so it's barium. No Roman numerals needed because it's always +2, and that's chromate. And then I recognize it's ammonium and nitrate. All right, those are all polyatomic ions. So if you don't know those, I'd highly encourage you to make the flashcards like you do and do them. All right, just know it makes your life so much easier because we're going to still have to do net ionic equations this semester. All right, I mean, I can ask you questions in chapters, the last 2 chapters, what was it, 18, 19, and they have questions. It's almost every chapter you need in there. Conversions, stoichiometry, balancing the chemical equation, naming, drawing a Lewis structure, to know if it's polar or not. All the other chapters, I can do that. So it's very cumulative. So I would highly encourage you to know those. All right. Now we're going to go the other way. All right, so I would recommend, all right, writing down. So sodium oxide, that's metal, non-metal. It's Na, we know it's group 1 metal. Oxide is O2 minus. Then come up with the formula Na2O. There's no shame in doing that. Now, will you always need to do that? I don't know. Maybe you will. Maybe you won't. Sodium peroxide. Well, peroxide is O2 2 minus, Na plus. So I have Na2O2. And there you go. Potassium cyanide. K plus, Cn minus, KCN. Copper 2 nitrate. Copper is 2 plus. Nitrate is NO3 minus. CuNO3 2. Selenium tetrabromide. I got a prefix, right? Tetra. So it's Se1 bromide 4. Lead 4 sulfide. Pb4 plus. S2 minus. Now, that's Pb2S4. That's technically accurate, right? That's technically accurate. But we prefer Pbs2. Easier to do the molar mass. It's the right ratio. And why do we do that with ionic compounds? Well, ionic compounds, right? They are an array of right positive, negative in 3 dimensions. Positive, negative. And so they're in a pattern. That pattern repeats itself. And so it's not just like a small discrete unit like a molecule. Selenium tetrabromide would be 1 selenium, 4 bromides together, and they just float around. That's it. All right? Or if they're a liquid or a solid or whatever they're doing. The ionic compounds are an array of ions to the end of the sample. So that's why we always reduce them. Copper 1 chloride. Cu plus, Cl minus, CuCl. Nitric acid. All right, so let's talk about the acids. If you remember, there's 2 types of acid name. There's binary acids or ternary oxyacids. So is there oxygen or not? All right. Hydro, no oxygen. No hydro, oxygen. So nitric acid comes from nitrate. us. So nitrate, which would be nitrate is NO3. It's minus, so I need 1 H plus. And I'm good. All right, that's the name of the acid. Diphosphorus, P2, pentaoxide, O5. So that's a little recap of naming. Hopefully that works for you guys. Now we're getting into number 4, some chemistry here. So you have a 0.755 gram sample of hydrated copper 2 sulfate. All right, and it looks like we're looking for X here. And determine the value of X is the question. So I got that much copper 2 sulfate with an unknown hydrate. And it was heated until it had changed completely to anhydrous copper 2 sulfate. All right, what does anhydrous mean? No water. There we go. No water. What's the value of X? All right, so I have CuSO4.XH2O. We're going to heat this thing. Give me CuSO4 plus XH2O. Now, if I start with 0.755 grams of everything, and I heat it up, and now I only have 0.483 grams. How many grams of water do we have? Well, I would take my 0.755 minus 0.483, 0.272. So now I have my mass ratio. Mass ratios are good, but I don't want mass. What do I need to do? I need to divide by the molar mass, right? So copper is 63.55 grams per mole, plus sulfur, 32.07, plus 16 times 4. I think that's 159.62. I believe that. I think that's right. Did I get all those numbers right? 3206 in this table. So that's not quite right. And copper is 63.55, 3206. I typically use 2 decimal points so that way we can be consistent. So I get 159.61. And water 18.02 grams per mole. All right, because 1.01 plus 1.01 plus 16. All right, so what do we get here? So 0.483 divided by my 159.61, I get 0.00303 moles of copper 2 sulfate. 0.272 divide 1802. I get 0.151, 0.0151 moles. Now we divide by the smallest, 0.00303. Looks like I get 1 and 4.98, which is 5. So it looks like my formula would be CuSO4.5H2O. And that's very common for copper 2 sulfate to have 5 waters. So that's that one. Number 4 in this case. So that's the law of conservation of mass with an empirical formula. All right. Bornite, which is copper, iron, and sulfur combined, is a copper ore used in the production of copper. When heated, the following reaction occurs. Now, if you notice, there's coefficients. So if they give you coefficients, it's balanced. If I give you coefficients, you can assume it's balanced and balanced properly. The only time it won't be if I made a mistake, like I did a typo or something. That's when it's, no, I'm not going to give you equations like, aha, you didn't check the balance correctly, so you're wrong. That's not me. All right, so if there's coefficients like this one, you can assume it's balanced. 2.5 metric tons of this ore, and you have excess oxygen, of course, and the process has 86.3% yield of copper. What much copper do you make? All right, that's the question right here. What mass of copper is produced? All right, so is this a limiting reactant problem? No. Why not? Because I have excess O2. So what I start with is this metric tons of this compound. All right. So I have 2.5 metric tons of CU3FeS3. Dots, we're used to dots. Now, we know 1 metric ton is 1,000 kilograms. And we know 1 kilogram is 1,000 grams. Right? And we put grams of CU3FeS3 on the bottom. 1 mole CU3FeS3 on top. Now, molar mass time. So copper, 63.55 times 3 plus iron, which is 55.85 plus 3 times 32.0, was it 7 or 6? This periodic table was 6. I get 342.68. All right. Then, now I'm in moles of my bornite, which is my iron ore, my copper ore. Now, we want to know how much copper we make. So we're looking for that one. So we know 2 moles of Cu3Fe(S3) makes 6 moles of Cu. We're not done yet. We know 1 mole of Cu is 63.55 grams of Cu. All right. And so if I do this math, 5 times 1,000 times 1,000 divide 342.68 times 6 divide 3 times 68.55 63.55, sorry, 63.55. I get quite a large number. I got 1854499.8 grams of copper. But that's my theoretical yield. I know that my percent yield is 86.3, so I times this number by 0.863. I get 1600433.3489. I have 3 sig figs, so this becomes 1.60 times 10 to the what? 1, 2, 3, 4, 5, 6 grams of Cu. That's it. All right, there we go. Yeah, now 6. Determine the molar molecular formula of the compound. That's 26.7% phosphorus, 12.1% nitrogen, and 61.2% chlorine. It has a molar mass of 580. Now, you might have been taught different ways to do this, and that's fine. I always start with the percent, assume grams, assume 100 grams, and go from there. I always do the empirical formula, then get the molecular. So we know we have 26.7 grams of P, 12.1 grams of N, and 61.2 grams of Cl. Divide by the molar masses. And phosphorus is what? 30.97. That's right. 30.97 grams per mole. 14.01 grams per mole. And 35.45 grams per mole. All right. 26.7 divided by 30.97. I get 0.862. 12.1 divided by 14.01, I get 0.864, which will be the same number. And 61.2 divided by 35.45 gives us 1.73. Divided by the small 0.0862. 1, and is that 0.0862? Oh, I have an extra 0 there. I'm sorry, guys. 2. So my empirical formula be PnCl2. And the molar mass of that empirical formula would be 30.97 plus 14.01 plus 35.45 times 2, which is 115.88. So I take my 580 divided 115.88 and I get 5. So we just multiply this by 5. P5 and 5Cl10. And there we go. And that's number 6. Again, if you have questions, feel free to ask. All right. Toluene, which is CH3C6H5, methylbenzene, burns an oxygen gas to produce carbon dioxide and water. Write the equation for this reaction and balance the reaction using whole number coefficients. What's the sum of all the coefficients? Don't forget any ones. All right, so CH3, C6H5 plus O2 goes to CO2 plus H2O. Now, that's technically a liquid, gas. Technically speaking, that's going to be a liquid most of the time. Because everything in chemistry land, which I call it, all our problems are in chemistry land. Chemistry land is 25 degrees Celsius. Well, at 25 degrees Celsius, water is mostly liquid. So, but if you put a G down, that is fine. All right, so balancing. All right, so I have 7 carbons, so I need to put a 7 there. I have 8 hydrogens, right? So I need to put a 4. All right, 5 and 3 is 8. 4 and 2 is 8. All right, oxygens. I have 4 and 14, 18. Put a 9 there. Now, what's the sum of all the coefficients? Make sure you have the 1 there. So it's 1 plus 9, 10, 17, 21. All right, because that 1 is there. Whether we write it or not, there's still 1 mole in front of that. The coefficient is 1. But there you go. That was probably a multiple choice test question at one point. All right, you guys are doing great. 8. 52 grams of acetylene reacts with 10 grams of hydrogen to produce ethane. How many grams of the non-limiting reactant remain at the end? Ooh. Reactant. So acetylene, C2H2 gas, hydrogen gas. You know hydrogen's H2 because it's diatomic. All right. Ethane, C2H6 gas. I have 52 grams and I have 10 grams. All right. So what I like to do here, divided by the molar masses, 2.02 grams per mole, and 12 and 12, 24, 26.05 2.04 grams per mole. All right, and let's see what we get. 52 26.04. I get basically 2.00 moles. And 10 divided 2.02, I get 4.95 moles. All right. So, is it balanced? No. Carbon is balanced. 2, 4, I need to put a 2 here, don't I? So that's now 2, 4, 6. Now it's balanced. There's 2. Right there it is. So now we got 2 carbons on both sides and 6 hydrogen on both sides. So now I like to take 2.00 moles divided by the coefficient of 1, give me 2. 4.95 divided by the coefficient of 2 is less than 2, isn't it? No, it's more than 2. 2 divided 2. Divided 2 is, clear. 4.95 divided 2. Yeah, 2.5. So that means my limiting reactants right there. I start with the 2 moles, and we don't worry about these. All right, so 2 moles. C2H2. Now we're looking for not how much hydrogen is left over in grams. So we know there's 1 mole of C2H2, 2 moles of H2. And then you know 1 mole of H2 is 2.02 grams of H2. So that gives me 8.08 consumed or used. So that means I start with 10 grams, subtract, that gives me what? 1.92 grams, which would be basically 2 grams H2 with 1 sig fig. There we go. That's it. All right. Number 9. All righty. Net ionic equation. So, if you remember solutions, there are electrolytes and non-electrolytes. There are strong electrolytes and weak electrolytes. So you're either a strong electrolyte, weak electrolyte, or non-electrolyte. If you're a strong electrolyte, you conduct electricity well, right? That's what it means. But what it means on the molecular level is that we separate completely. Weak electrolytes separate a little bit, non-electrolytes separate at none. So what are the strong electrolytes? Ionic and aqueous, soluble salts, strong acids, strong bases. That's it. So let's talk about those. So, right? So ionic and aqueous are strong acids, are strong bases, which the strong bases are ionic and aqueous. These are all strong electrolytes. So let's review the acids. HCl, HBr, HI, the 3 middle halogens. H2SO4, HNO3, HClO4, HClO3. Those are our strong acids in this course. Are there more strong acids than that? Of course. But those are our strong acids. All right. So, does sodium chromate break apart in solution? Yes or no? Well, it's an ionic compound because I have a metal polyatomic ion, and it's aqueous. So yes, it's ionic and aqueous. So that means I get 6 Na plus 3 CrO4 2 minus. Does aluminum bromide break apart? Well, it's ionic and aqueous, so yes, 2Al3 plus 6 Br minus. Have an arrow here. Does aluminum chromate break apart? No, it's a solid. Al2 CrO4 3 solid plus, does sodium bromide break apart? Well, yes, it's ionic and aqueous. 6 Na plus 6 Br minus. All right, spectators. Well, we know this guy is what's being made. So that means I need aluminum and I need chromate. That means sodium should be a spectator ion and bromine should be a spectator ion, and they are. All right, so my net ionic equation would be 3 CrO4 2 minus 2 minus aqueous plus 2 aluminum, giving us our solid product of aluminum chromate. And there's your net ionic equation. So ionic and aqueous, strong acids, strong bases. And the strong bases are the group 1 and 2 hydroxides. I think when we get to chapter 15, we add to the definitions, but right now that's where we're at. Okay. All right. Number 10, dilution. This is our favorite Chem 1 formula. If you remember the dilution formula, M1V1 is M2V2, right? So, what's the molarity is the question. So that's M2, right? So remember, we use this when there's no reaction. So M1, 3.0 molar. V1, 25.0 milliliters. Equals M2, we don't know, and 150 milliliters. So M2 would be 7.5, 3 times 25 divided 150.5, and I have 2 sig figs, so 0.50 M. All right. Acetic acid, which I'll probably start writing CH3COOH for us. All right, but it doesn't matter. If you write it as HC2H3O2, I'm fine. All right, number 11. Number 11. You have 10 milliliter sample of vinegar, and it's titrated with 0.5062 molar sodium hydroxide. 16.58 milliliters is required to reach the equivalence point. What's the molarity of the acetic acid? Great question. All right, so acetic acid, and it's written this way: HC2H3O2 plus NaOH goes to switcheroo, right? Neutralization reaction, switch adant partners, NaC2H3O2. Sodium salts are soluble, and water liquid. Excellent stuff. Balanced? Yes. Chances are you've had this reaction in Chem 1. So we have 10 milliliters. I don't know the molarity. We have 0.5062 molar, which is large, 16.58 milliliters. There we go. Okay, there we are. So, the limiting reactant is the sodium hydroxide. I start with my 16.58 milliliters. Now remember, the molarity, all right, 0.5062 moles of NaOH per 1,000 milliliters, right? 1 liter is 1,000 milliliters. Then we know it's 1 mole of NaOH to 1 mole of HC2H3O2, acetic acid. So 658 times 0.5062. What do I get? I get 0.00839. And I have to divide that by our 10 milliliters. Which is 0.01000 liters. So it looks like 8.829. Excellent. Again, if you have questions, ask. Okay. If you have questions, feel free to ask. All right. How much more do we have here? We got that one. Ooh, that's a good one. Oh, yeah, good. All right. Oh, wow. We got quite a bit. Okay. Very good. Twelve. Hydrochloric acid, 75 milliliters, 0.25 molar, is added to 225 milliliters of barium hydroxide. What's the concentration of the excess H plus or OH minus in this solution? This is a good problem because we're going to do this. All right, we will do this semester a lot. So HCl plus BaOH2 going to BaCl2 plus H2O. Is it balanced? No. So I have 2 in front of HCl, and I believe I just need 2 in front of water, right? And we have 75.0 milliliters, 0.250 molar, 225 milliliters, and 0.0550 molar. Okay. All right, so now we have to find the limiting reactant and then find the excess. All right. So molarity times volume. If you guys remember, I take my 75.0 milliliters multiplied by, for every 1,000 milliliters, I have 0.250 molar, and 225 milliliters, 1,000 milliliters, I have 0.0550 moles. All right, so what do we get here? I get I get 0.01875. I get 0.01235. I know that's extra sig figs. All right, now limiting reactant. I'm going to take my 0.01875 divided by 2, divided by the coefficient, give me 0.0094, and 0.01235 divided by 1, 0.012. So that means HCl is my limiting reactant. And we will start all of our calculations with that. So I have 0.01875 moles of HCl. And we know it's 2 moles of HCl, 1 mole of BaOH2. Right? So that's 0.009375 moles of BaOH2. Parentheses. All right. Now, here's the deal. I'm looking for the excess, in this case, OH ions, concentration, excess OH ions, right? So I need moles of hydroxide over volume, over the total volume. All right, so we know our volume, I know I have 0.009375 moles of BaOH2, and my volume is 75 milliliters plus 225 milliliters. All right? So we're going to take this. We know that for every 1 mole of I messed up. I'm sorry, guys. I messed up. This is what we used. So I got to subtract. I got to take my 0.012375 moles, subtract my 0.009375 moles, we got 0.01235 minus 0.003. There we go. Almost really blew the problem. Sorry, guys. All right. So 1 mole of barium hydroxide, 2 moles of hydroxide, and 1,000 milliliters per 1 liter. And that should give us our answer. So So 0.003 times 2 divide, it's actually 300 times 1,000. 0.02. Do I have 2 sig figs or 3? 3. So 0.02. That's a tough Chem 1 problem. All right. So that if we follow that, we found the limiting reactant. We take the molarity times the volume. Wrote the balanced chemical equation. Molarity times the volume to get moles. Found the limiting reactant. Found how much barium hydroxide was used. Then found out how much barium hydroxide was left. And then figure out how much hydroxide was left from the barium hydroxide divided by the total volume to get the concentration. All right, and that's going to be important for pH problems when you do the pH problems. All right, let's see here. Okay, classify. All right. Well, this is just a multiple choice question. Which one had the right? So strong acids. Let's look at strong acids. That's a strong acid, strong acid, strong acid, strong acid, strong acid. The other two are weak. Strong base, 1, 2, 3 strong bases. Weak acid. Let's use a different color. Let's use green for the weak acids. HF, HCN, HNO2, that one, HNO2, and a salt. Ionic, 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 ionic. All right, so which one has something highlighted in everything? Nothing. Do we... Oh, it just said base. Huh, base. Doesn't say strong base, it says base. Base, base, base. So the answer would be then B. That works. So let's write that down. Weak, weak, strong, strong. We're going to learn that cyanide becomes a base. So weak and strong. Good. All right. There's 13. An 8-liter vessel contains 5 atmospheres of hydrogen, 3 atmospheres of helium, 2 atmospheres of oxygen, and a pressure of 10 atmospheres. What's the mole fraction of oxygen? Well, if you remember mole fraction of O2 would be the moles of O2 all over the total moles. All right. And then we got 8 liters, 5 total pressure. So partial pressure. The pressure of O2 is equal to the mole fraction of O2 times the total pressure. Right. Okay. So we have we have 5, 3, and 2. So I have 2 atmospheres. Oh, it doesn't tell us the moles. Oh, okay. PV equals nRT. Does temperature change at all in this? No. Does R change? No. Does V change? No. So right now, pressure is proportional to N, but we want them, so we don't need to know the total moles, we just need to know the mole fraction. So it's still going to be 2 atmospheres. Yeah. All over 5 plus 3 plus 2 over 10 atmospheres, which would be 0.2. Now, could we find the number of moles? Probably not. So we have to do it that way. We have to do pressure is proportional to moles for that. That's fun. There we go. All right. 15. A student adds 4 grams of dry ice to an empty balloon. What will be the volume of the balloon at STP? Well, remember, STP, this means 22.4 liters is 1 mole. All right. So if I have 4.00 grams of CO2, we know that 1 mole of CO2 is 32 and 12, 44. 44.01 grams of CO2. And 1 mole of CO2 is 22.4 liters at STP. Let's see. 4 divided 44.1 times 22.4. 2.04. 2.04 liters. There you go. So 4 grams is not a lot. So that's 2 of these Nalgene bottles. That's pretty good. Let's see here. All right. 35 grams of liquid water near its boiling point at 91 was poured carefully into a mixture of 50 grams of ice and 35 grams of water at 0, where all the ice melted. Or ice melt, doesn't say all the ice. What mass of liquid water is present at the end? So does all the ice melt? All right, so if we remember these types of problems, right, you're going to have hot water, and then you got ice and water. And they both have an amount of energy. Energy and energy, right? In the law of conservation of energy, the energy lost, Q lost, it's negative, is the Q gained, right? The heat lost, heat gained. All right? So all the water can do is cool down. And if there's still ice left, the final temperature would be 0. All right? So for the hot, we're going to have negative Q, right? So all this means is it's exothermic. So Q equals mc delta T, right? So Q would be the mass, 35 grams. Specific heat of water is 4.184 joules per gram degrees Celsius. And it goes from 91 to 0. So 91 degrees Celsius. All right, so the heat that the water can give off, the hot water can give off, would be 35 times 4.184 times 91, which is 13,13326.04 joules. That's the heat released. That's the maximum amount of heat it can release. It might not need all of that. So now let's look at the ice. Q equals delta HF times the mass, right? Because that's a melting formula. All right, and I have 50 grams of ice. So let's see. 13,326 joules equals 333 joules per gram, that's delta HF, times the mass that melts. Well, how much melts? 40. 40 grams of ice melts. All right, so 40 grams melts. All right, so I start. I have 35 grams of hot water. I have 50 grams of ice. And I have 35 grams of that water too. And just 35 grams of water. All right, the ice is going to lose 40 grams. So we're going to have 10 grams of ice, right? And so I'm going to have the 35 grams of the cool water plus the 40 grams for the melted ice plus the 35. So that's 35 is 70, 110. Because altogether they need to add up to 120, right? Because I have 120 grams total. I don't lose any mass. Right, so that's 70 plus 50, yeah, 120. And I do 10 grams of ice and 110 grams of water. So most of the ice will melt, but not all. All right, so there's your heat transfer problem. All right, let's see, what else do we have here? Ooh, if you remember this, what substance is delta HF equals 0? These are elements in their standard state. So I want element in standard state. So, periodic table, especially all these web elements or P table or whatever they are, right? It'll tell you their standard state. There's 2 of them that are liquids. All right, 2 of them that are liquids. Okay, most of them are solids. Some of them are gases. Oxygen. Oxygen is diatomic, so it's not oxygen. SO3 is not an element. F is diatomic. Water is a compound. Ammonia is a compound. HCl is a compound. Phosphorus is an element. Probably. Copper is an element, but copper is not liquid. H2 is not a solid room temperature, and methane is a compound, so it is P4. And phosphorus does come in P4. That's elemental phosphorus is P4. All right. How are we doing here? All right, so we don't have the. Yes. All right, calculate the standard enthalpy of formation. Of HF, given the following information. So that's my reaction. So delta H, if you remember, delta H of the reaction equals the sum, the standard enthalpies of formation of products, minus the sum, the standard enthalpies of formation of the reactants. Wow, all right. So I know delta H of the reaction plus 538 kilojoules. Products, H2 and F2. Reactants, 2 times HF. Well, both of these are 0 because they're elements in your standard state. So that means I get plus 538 kilojoules is equal to negative 2 times whatever HF is. So HF happens to be, well, the delta H for HF. What is that? Negative 269. And there we go. All right, we're doing pretty good on time here. I want to get done soon. So it's negative 269 is what I got. Again, ask questions if you have questions. 18. We're not going to actually do this, I don't think, in class. So if you just remember, delta H for the reaction is equal to the energy of bonds broken minus the energy of bonds formed. All right, so bonds broken minus bonds formed. So we're going to skip 18. Feel free to do it. All right, let's see here. Which of these are polar? So this is important for our first chapter, because chapter 11, intermolecular forces, we need to know if molecules are polar or not. All right, okay, and so we're going to review polarity tomorrow. All right, I will tell you that B is polar, T is polar, and SiO2 is polar. Is it polar? No, it's not. Silicon is polar. Yeah, that's going to be, the way we're going to draw is going to be linear. It's not going to be polar. All right, so now, yeah, there's those two. All right. So we're going to review this tomorrow, polarity. All right. So let's do 20. Let's recap. Just draw. IF2 minus. So iodine has 7 valence electrons. Fluorine has 7, and there's 2 of them. So that's 20, and then there's the minus 1. So that's another add 1. 21 plus 1. 22 valence electrons. All right. So if you remember the table here, group 1 has 1 valence electron. 2 is 2. Skip the transitions because they vary, but it's usually 2 or 1. 3, 4, 5, 6, 7, 8 valence electrons. Of course, helium only has 2 valence electrons. All right. Iodine is in the central because fluorine cannot be in the central. All right, fluorine only makes 1 bond. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, right? Extra electrons go in the central as lone pairs. All right, so iodine can violate the octet rule because it's in the 3rd period or below. So it looks like I have 3 pairs that are around the central atom. Lone pairs, 5 pairs total. All right, so drawing Lewis structures, fun stuff. SF4, I want the shape and the electron pair arrangement. So electrons for SF4, sulfur has 6 electrons, and 7 times 4, so that's 28 and 6. That'd be what? 44 electrons, is that right? No, 34. 34. All right, isn't that right? So let's go look at the table. Sulfur has 6 valence electrons. Fluorine has 7. All right, so 7 times 4 plus 6. 34. All right. Central atom is not fluorine, so S. 1, 2, 3, 4. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I have extra electrons. They probably go on the sulfur because fluorine's not going to violate. So the electron pair arrangement, I have 1, 2, 3, 4, 5 pairs. Trigonopyramidal. The shape, that shape would be seesaw. Not common. It's not tetrahedral or bent or trigonoplanar or something like that. All right, and so that's that one. That was a tough one. Hybridization. I don't know if you remember hybridization. All right, from valence bond theory. All right, so I would draw it. 8 for a xenon plus 7 times 4. Right? So 28 and 8, 36 electrons. Central atom is the xenon. All right, bond 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. It's good. Electron pairs 1, 2, 3, 4, 5, 6 pairs. It's octahedral. That means it's sp3d2. Whether that exists or not, doesn't matter. That's what the book says hybridization is. So that's hybridization. We're almost done. We'll be done in a couple minutes. Oh, last problem. We'll be done after this one. All right, last one for today. Because there's a lot of review. Hopefully this was not like scaring you. I don't want to scare you today. I want to just recap things and bring things back to memory. All right, again, we're going to teach everything we need to teach. It's not like, all right, but hopefully this came back. All right, electrons. Nitrogen is 5, and there's 2 of them. Oxygen is 6, so that's 16 electrons. All right, so 2, 4. Why is it only all right? 6, 8, 10, 12, 14, 16. Well, I can double bond both sides. That works out. I could triple bond this end. Or I'm going to do this a different one. I don't know why it ends in the middle there. But okay. All right, so formal charge. If you remember formal charge, it's the charge the atom would have if everything was shared evenly. So each electron in the bond, if there's a 2-electron bond, each atom gets 1 electron. So for nitrogen here, we're going to break this bond. So we have 1, 2, 3, 4, 5, 6. It has 6, brought 5. So I gained an electron. So this nitrogen is formally -1. The nitrogen in the middle has 1, 2, 3, 4. It brought in 5. It's technically formally +1. Oxygen has 1, 2, 3, 4, 5, 6. Has 6, brought 6. It's 0. Let's use a different color. So that's pretty minimal. Because we want to minimize formal charge, right? Let's look at the central one. 1, 2, 3. 1, 2, 3, 4, 5. Has 5, brought in 5, it's 0. Nitrogen in the middle. 1, 2, 3, 4. Plus 1, because it has 4, but it brought in 5. Oxygen. 1, 2, 3, 4, 5, 6, 7. Has 7, brought in 6. It is -1. Okay. The last one. Nitrogen here. 1, 2, 3, 4, 5, 6. It's -1. Oxygen in the middle. 1, 2, 3, 4. Plus 2, brought in 6. Nitrogen in the end. 1, 2, 3, 4, 5, 6. It's also -1. All right. So those are our formal charges. All right, just how many valence electrons I brought in versus how many I have. I share each bond evenly. So the worst one is probably that one. Why is that the worst one? Because oxygen is the most electronegative. If oxygen is the most electronegative, it's probably more likely to be negative. And since oxygen is +2 and nitrogen is -1, it's probably not the best example. The best one between the other two would probably be the center one, with oxygen being -1. That doesn't mean NNO that are double bonded is bad. It's a valid resonance structure. It's just not as equal, but it's not bad. There you go. So there's the review. Tomorrow at 11, I'm going to start reviewing polarity, electronegativity, polarity, and then starting intermolecular forces. So that'll be tomorrow's lecture. For you guys, make sure you do your digital scavenger hunt, because that gets you your lab kit. Make sure you have your lab kit ordered. If you have not done so, you can go to the bookstore and get them, especially if you're a financial aid, or they might just give you a code, like a voucher. But or you can go right to eScience and get it, and then do your Chapter 11 reading worksheet. Those are the first two things to do. Does anybody have any questions? Any questions, guys? I know there's a lot today, so. Oh, something kind of happened. All right. Well, if there's no questions, I will see you guys tomorrow. Remember, I can be reached by email. All right. Go get some lunch, and we'll talk to you then. All right, guys. Take care.